Hello, good day. This topic is all about measurement and significant figures. As we've covered in the previous lesson, measurement is the process of comparing an unknown quantity with a standard unit. In science, it is how we make observations more objective and reliable. Without measurement, experiments would be guesses. Imagine baking a cake without measuring the ingredients or building a bridge without knowing its length. Things would easily go wrong. Measurement is our way of bringing order and accuracy to the world. It helps us describe, compare, and communicate information clearly, whether in daily life or in science. Regardless of the system of units employed, scientists must be aware of three principles that govern the proper use of numbers, and they are accuracy, precision, and significant figures. We'll talk about them one by one. Science is based on experimentation that requires good measurements. The validity of a measurement can be described in terms of its accuracy and its precision. Accuracy, it refers to the closeness of the experimental values to the true value. Precision, on the other hand, it refers to the closeness of the individual experimental values to one another. So just a simple difference. If you talk about accuracy, the closeness or the nearness of all the values to the established actual true value. Whereas precision, it refers to the closeness of individual values to each other, regardless of the true value or established value. Suppose the true value of wind speed is 25 meters per second, and we have two anemometers, A and B, and they take 5 wind speed readings each. Anemometer A reads 25.50, 25.69, 25.52, 25.58, 25.61 meters per second. We take the average of all readings and we get 25.58 meters per second. Anemometer B, on the other hand, reads 26.3, 24.5, 23.9, 26.8, and 23.6 meters per second. We get the average of all readings, 25.02 meters per second. So the question is, which anemometer has more precise readings? I'll give you 5 seconds to think about it. So what's your answer? Remember, precision is the closeness of individual readings or value to one another. And we can see here that anemometer A has precise readings because all of the readings in anemometer A is just 25, and but then they only differ in terms of the decimal places. Whereas anemometer B has values of 26, 24, 23, 26, and 23. They are a little bit far from one another. That's why anemometer A has more precise readings. Which anemometer has more accurate average reading? I'll give you 5 seconds to think about this. Okay, your answer is yes, it is correct. While anemometer A has more precise readings, but anemometer B has more accurate average reading. So remember, accuracy is the closeness of the values to the true value. And the true value has been established in the problem that suppose the true value of wind speed is 25.00 meters per second. And in terms of average, anemometer B is closer compared to anemometer A. Anemometer B has 25.02, whereas anemometer A has 25.58 only. Okay? We can actually, in terms of analogy, we can actually present accuracy and precision like in a game of darts. Have you played the game of dart? Yes, in a game of dart, we have the dart pins, the one that you throw, and the dart board. In the middle of the dartboard, we have the bullseye. So pictures from left to right shows combinations of accuracy and precision. First one, picture at leftmost. This picture shows you high accuracy and high precision because all of the dart pins, let's just say the dart pins are the individual readings. All of the individual readings are close to each other, that's high precision, and close to the true value. Let's just say the bullseye is the true value. So we can say that this is high accuracy, it has high accuracy, and it also has high precision. Next picture shows you low accuracy and high precision. Low accuracy because all of the individual readings are far from the bullseye. High precision because all of the individual measurements are close to one another. The third picture shows you high accuracy but low precision. High accuracy because the individual readings are closer to the bullseye, and one hits the bullseye actually, but it has low precision because they are far apart. The last picture shows you low accuracy and low precision because they are far from one another and they are far from the true value. Now, no measurement is ever perfect. You have to put that in your mind, which brings us to the idea of uncertainty. Before we talk about uncertainty, it's very important to represent the measurement in terms of its quantitative value. So we will be talking about significant figures in this portion. The number of significant figures in a measurement indicates the precision of the measuring tool. So the more precise the measuring tool is, the greater the number of significant figures it can report. So I'm showing you here three rulers. One ruler at top shows you the in measurements of decimeters, and the second picture in the middle shows you the in centimeters, and the last shows you in millimeters. So if we compare the three rulers, the more precise, on the most precise ruler is the last ruler because it has many ways or greater numbers of significant figures compared to decimeter here at top. You can just guess if ever one the tool or the thing that you are measuring falls between 0 and 1. So the measurement is just an estimate. Unlike in millimeters, the millimeter ruler, so it has clear measuring lines whenever a thing falls between, let's say, 10 or 10 and 20. There are available measuring lines that you can use to measure or to determine the length of a particular object. So I'm talking about what if we really have a thing that we're going to measure using the rulers. So let's say we have a banana, and these three bananas are identical. So three metric rulers are shown. The first ruler is in decimeters and can measure zero point 0.3 decimeters. That is just a rough estimate actually. You can have a different measurement if you think that this is not 0.3 decimeters. The second ruler is in centimeters long and can measure 3.6 centimeters. Again, this is just an estimate. You can have your own guess. And the last ruler is in millimeters and can measure 36.5 millimeters because it has many available measuring lines, and they can estimate more precisely as compared it can estimate more precisely as compared to the two rulers above. So you see, the more measuring lines available, the more accurate is your measurement. So again, I've said that no measurement is ever perfect. No single measurement is perfect. So that brings the idea of uncertainty. Presentation of quantitative data is very important in a scientific work. Every measurement is uncertain because there are many available zeros. If you write all the zeros to the right of a particular number, you can go on for eternity or infinity. So we must use numbers that are meaningful only. Suppose that there are three persons and they're measuring the height of a toy using the ruler at right. So you see this ruler at right. One person reports 4.56 centimeter. Another person reports 4.55 and another person reports 4.57. So they are different, no? The three measurements are different in terms of their last digits. These last digits actually they are more of a guess and therefore they are uncertain. Let's zoom in. We can see this ruler and they reported 4.56. You can see it here, 4.55 and 4.57. The millimeters part of the ruler above shows you 1 millimeter only. So you can just have 4.1, 4.2, 3, 4, 5, but the second digit is more of a guess. And that's why we said that every measurement is uncertain because no tool can ever have infinite numbers of measuring lines. But we can actually present uncertainty in terms of value. We can express it in terms of percent. So one method of expressing uncertainty is as a percent of the measured value. If a measurement, let's say A, is expressed with uncertainty, let's say sigma A, the present or the percent uncertainty is equal to uncertainty divided by measurement times 100%. The uncertainty or sigma A is expressed as plus or minus symbol and the largest difference between the value and individual measurements. So uncertainty, that part in the numerator, is taken by subtracting the largest value and the minimum value, or subtracting the largest value and each of the individual measurements if the minimum value is not available. Example, let's calculate percent uncertainty of a bag of apples. A grocery store sells 5-pound bags of apples. You purchase 4 bags over the course of a month and weigh the apples each time. You obtain the following measurements. Week 1 weight is 4.81 pounds. Week 2 weight is 5.3 pounds. Week 3 weight is 4.9 pounds. And week 4 weight is 5.4. So what's the percent uncertainty of the bag's weight? Remember the formula? All we need to do first is subtract the given measurement, in this case 5 pounds, with each of the given value every week. Whichever results to the greatest difference, that would be our uncertainty or sigma A in the numerator for the formula. Our A here is 5 pound, and the sigma A for the numerator would be the greatest difference between A and each of the measurement. Okay, so let's do this. So we will subtract A, which is 5 pounds, to every measurement per week to give the uncertainty. So for week 1, 4.81 minus 5 is equal to negative 0.19. For week 2, 5.3 minus 5 is 0.3. Week 3 is negative 0.1. Week 4 is 0.4. So among the 4 measurements, regardless of the sign, you don't need to consider the sign for this because the uncertainty is only plus and minus. And when we say the greatest difference, that is the distance of a number from another number. So the sign here doesn't matter. So among the 4 measurements, which has the greatest difference? Of course, it is in week 4, 0.4. 0.4 is the largest difference for every week's measurement. So therefore, 0.4 is our sigma A, and our A is 5 pounds. So let us substitute all of these values in our formula. So percent uncertainty is equal to uncertainty divided by measurement. In this case, the uncertainty is the largest difference, which is 0.4, divided by the measurement 5 times 100%. That would be 8%. Therefore, the bag of apples weight is 5 pounds. When you present your uncertainty, let's make use of plus and minus sign. plus and minus sign, 8%. It means that the bag of apple can exceed up to 8% above and 8% below. So plus and minus sign actually denotes the range of values because we are not sure that we get 5 pounds every week exactly. It can go above 5 pounds and the maximum allowed measurement is 8% of 5, and we can go below 5 pounds and the minimum value is 8% of 5 below. So that is the meaning of plus and minus. Let's solve another problem. Let's calculate the percent uncertainty of a triple beam balance. The uncertainty of a triple beam balance is 0.05 grams. What is the percent uncertainty in a measurement of 0.25 kilograms? So based from the problem, the uncertainty is already given. Remember in the formula, the uncertainty is sigma A, the numerator. And the 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 measurement is 0.25 kilograms. That is our A for the formula. But if you notice, the two measurements are in different units. One is in gram, one is in kilograms. So first, we have to convert either of the two. So I decided to convert 0.25 kilograms into grams. If you want to convert 0.05 into kilograms, the answer would be the same. So what if 0.25 is converted into grams? That would be 250 grams. And from this point onward, we can substitute all the values in our formula. Percent uncertainty is equal to uncertainty divided by measurement. In this case, our uncertainty is 0.05 and our measurement is 0.25 kilograms in gram. That would be 250 grams times 100%. The answer is 0.02%. Thus, the measurement of 0.25 kilograms has an uncertainty of 0.02%. That means if that measurement is taken from the triple beam balance, the value can exceed 0.02% above 0.25 kilograms and 0.02% below 0.25 kilograms. Okay, so that would be all for uncertainty. But what if there are many measurements? Can we add percent uncertainty for every measurement? Let's say you have five units and all of the units have each percent uncertainty on its own. Can we add all the percent uncertainties? So if the measurements in the calculations have small uncertainties, just a few percent or less, then the method of adding percents can be used. This method says that the percent uncertainty in a quantity calculated by multiplication or division is the sum of the percent uncertainties and the items used to make the calculation. So you can just add the percent uncertainty if you multiply the numbers with percent uncertainty. And that is also applicable if you divide the numbers with percent uncertainties. Example, a floor has a length of 4.00 meters with 3% uncertainty and 3.00 meters width with 2% uncertainty. So if you notice, the two dimensions has its own uncertainties. If we multiply these values, all we need to do with their uncertainties is add them. So the formula for area, we know it is length times width. So 4 meters, 4.00 times 3.00 meters, that would be 12.0 meters. How about their uncertainties? We just add 3% plus 2%, that would be 5%. So if you multiply numbers with uncertainties already or divide them, all you have to do with their uncertainties is add them all. Okay, so that will be all for uncertainties. But to deal with uncertainty and show the quality of measurements, we must follow the rules of significant figures. If you notice, in the dimension 4.00 meters, and 3.00 meters, they both have two decimal places after the decimal point. But our answer only has one decimal place, 12.0. So what happens? So let's learn now how to present our calculations following the number of significant figures. Suppose a known substance has a volume of 2,563 ml or milliliters, and you'll have to apportion the substance into seven equal volume. What would be the volume of each portion? So simply, the problem is asking us to divide 2,563 into 7 portions. So if you're using your calculator, the value would be 366.142857, 142857, and this repeats in infinity. So what's the better approach to show the answer to this question? Because if we really write all the numbers, it is impossible for us to present them all because this is repeating and non-terminating. So the decimal place goes through infinity, but the better answer would be 366.1 milliliters. Why? Because we're following the rules for significant figures. So what are the rules for significant figures? In the next slide, we will be presenting all the rules for significant figures. From this time onward, we will be using the rules for significant figures in every calculations that we do in this subject. Rules for significant figures, rule number one. This is for non-zero digits. Non-zero digits are always significant, meaning they're very important. How many significant digits are in the following number? 274. The answer is yes, 3. If we count all the digits and we notice that all of these digits are non-zero, then we have 3 significant digits or 3 significant figures. How about negative 25.632? We have 5 significant digits. How about 8.987? We have 4 significant figures. So again, non-zero digits are always significant. Rule number 2. How about 0 between non-zero digits? All zeros between non-zero digits are always significant. So how many significant digits are in the following numbers? 504. This has 3 significant figures. 0 here is in the middle of two non-zero. Therefore, it is significant. It is counted. How about 60,002? The answer is 5 significant digits because still all the zeros here are in between two non-zero digits. How about 9.077? Obviously, it has 4 significant figures. Rule number 3 for trailing zeros. Trailing zeros are zeros, successive zeros after a number. All final zeros to the right of a decimal and a non-zero digit are significant. So we have two conditions here. In order for zeros to be significant, they must be written to the right of a decimal point and to the right of a non-zero digit. Example, how many significant figures are in 2.0? There are 2 because 0 here is to the right of a decimal point and to the right of a non-zero digit 2. How about 1.50? There are 3 significant digits. How about 105.0020? The answer is 7 significant figures. The 0 between 1 and 5 is significant as said in rule number 2 and also in between 5 and 2 as as the previous slide rules as the previous slide's rules, and the last 0 digit here is significant because of rule number 3. How about trailing zeros and underline zeros? All zeros to the left of the decimal point. This time, what about if the 0 is to the left of the decimal point? All zeros to the left of the decimal point and to the right of a non-zero digit are not significant. To indicate its significance, an underline is written. left of the decimal point, and right of a non-zero digit. For example, 5,000. How many significant figures are in this number? There is only one. 5 is the only significant figure here because the zeros after 5 are zeros to the left of the decimal point. We don't necessarily write a decimal point, and to the right of a non-zero digit, 5. And that's why they are not significant. 150 only has two significant digits. 10,500 has five significant figures. This time, if we underline the zeros to the left of the decimal point and to the right of a non-zero digit, they will become significant. So 10,500 has five significant figures. Okay, how about placeholder zeros? The zero that comes before a decimal point. All zero that acts as placeholders are not significant. Another way to say this, zeros are only significant if they are between significant digits or the very final digit after a decimal point. So in 0.25, there are only two significant figures because 0 here is just a placeholder 0. And 0.000005, in this case, there is only one significant figure. There's only one significant figure because all of the zeros that comes before 5 are not significant. Remember, zeros are only significant if they're in between significant digits or the very final digit after a decimal point. Okay? So, in rule number 4, if you recall, 5,000 has only one significant figure. But how to express it in a way that it would really become 5,000? In mathematics and in science, we have to use scientific notations in order for all of the zeros there are accounted for. In scientific notation, we've learned this in our previous lesson, all numbers reported in front of the multiplication sign are significant, including the zeros in front of the multiplication sign. So you can just disregard the times 10 raised to a power. Okay, for example, 6.538 times 10, 10 raised to negative 5, we have only four significant figures. You must not include in counting the multiplication sign and the 10 raised to a number. So that this is also the same rule that applies to the following numbers after it. 3.04 has three significant figures. Negative 250 has three significant figures. Okay, the last rule for significant figures. How about exact numbers? Exact numbers are numbers um, that are very sure. There are constant numbers. There are numbers taken from counting. If you personally counted all of the objects and you reported them as such, they are considered exact numbers. All the constant numbers in science and math, they are also exact numbers. And exact numbers are treated as infinite numbers, and therefore they must not be included in counting for the significant figures. For example, 12 pieces in a dozen is a constant, and therefore the significant figure for this is infinite, meaning you don't need to count it or include it in your calculations. For example, you're asked to count the number of students inside the classroom and you counted them as 10 students. Then 10 is an exact number. You don't need to apply the rules in significant figures for this. 3 feet in a yard is a conversion factor and you don't need to include this in your counting for the significant figures. Okay? So the next part is how about if we add numbers? How many significant figures? If we add, multiply, divide, or subtract, how do we report significant figures from the calculations? Addition and subtraction has their own rule, Multiplication and division also have their own rule. For example, let's learn first the rules for addition and subtraction. In addition and subtraction, you have to calculate first any given mathematical sentence or statement. The final answer must contain the decimal places following the fewest decimal places after the decimal point from the given problem. So you have to take note of this. The final answer must have the fewest decimal places after the decimal point following the given number from the problem. Example, 3.45 plus 2.063 plus 5.1. So if you calculate this using your calculator, or you add them, if you already calculate if you already written this in your paper and then you calculated the value, that would be 10.613. But this is not the final answer. We must apply the rules of significant figures or digits in addition and subtraction. The rule is fewest decimal place, and we have to look at each of the number given in our problem: 3.45, 2.063, and 5.1, and determine the fewest decimal place. The fewest decimal place is in 5.1. There's only one decimal place after the decimal point. In other words, the final answer must follow it, and it should only have one decimal place after the decimal point. So the value 10.613 must be 10.6. So um we rounded off, or rounded the number to 10.6, and the rules for rounding off will be applied in addition, subtraction, multiplication, and division. Simple rule is, if the number to be dropped is 5 and above, you have to add 1 before that number. Or if the number to be dropped is 4 and below, then you have to retain the number. In this case, the number to be dropped is 1. That's the number after 6. Since 1 is is below 5, meaning 4 and below, so the number 6 must be retained. However, if that value is 5, 6, 7, 8, 9, so you must add 1 to the number before it, which is 6. So that becomes 10.7 if that's the case. So what about this? 0.92 plus 3.080 plus 5.0. So if you calculate this, this would be exactly 9. And then this is not the final answer because it must contain a decimal place following the fewest decimal place from the given problem. So the fewest decimal place is in 5.0, and that only have one decimal place, 0. So therefore, the correct answer must be 9.0. So you have to follow the fewest decimal place. How about in multiplication and division? First, calculate any given mathematical sentence, and the final answer must contain the number of digits following the fewest significant figure from the given problem. So this time, we don't need to follow the fewest decimal place, but instead, we have to follow the fewest significant figure from the given problem. In this case, you must memorize the rules in significant figures as presented before this slide. So for example, 5.32 times 6.78. If you use your calculator, the answer is 36.82896. So this is not the final answer yet. We must first determine the number with the fewest significant figure in the problem. So 5.32 has 4 significant figures. 6.78 has 3 significant figures. So therefore, the fewest significant figure is in 6.78 because it only has 3 significant figures. Therefore, our final answer must only contain three significant figures. So you have to count from the left. So 3, 6, and 8. So these are the three first significant figures in the answer. So you have to drop 2 for this to give 36.8. So 36.8 only has three significant figures following 6.78's significant figure. How about if we divide the numbers? 0.80 divided by 0.262. First, let's calculate it using your calculator. We come up with 3.053435115. And then this is not the final answer yet. We have to follow the fewest significant figure from the given problem. So first, 0.80 has only two significant figures. 0.262 has three significant figures. Therefore, the final answer must contain two significant figures following 0.80. Okay, so the final answer must be 3.1. 3.1 because if you drop 5 and 5 is according to the rules of rounding off, 5 and above, if you drop them, you have to add 1 to the number before them. So 0 plus 1 is 1. That's why 3.1 is our final answer. But what about when we combine the operations? When we combine the operations, a simple rule would be following PEMDAS. PEMDAS is an acronym of the order of operations in mathematics. The first order must be, or the first one to be calculated must be within P. P means parentheses. Whatever numbers are inside the parentheses, you must first calculate them. After that, E stands for exponent or roots. After that, MD. MD is a twin. And whichever comes first, multiplication or division, they must be calculated first. And lastly, AS stands for addition and subtraction, and they would be of last priority. So for example, 14.84 times 0.056 minus 8.02. First, we have to apply the rules. In PEMDAS, we have to calculate 4.84 times 0.56 first. So the answer for that is 8.3104. Do not apply the rules in significant figures yet. Always apply them in your final answer. Do not apply it along the way or in between calculations. So first, the answer is 8.3104. Then subtract it with 8.02. So the answer is 0.2904. And after that, the final answer shall contain two decimal places following the addition subtraction rule. So apply the rule. The rule is apply the rule in the order of operation you use. Do not round off along the process. Always round off in the final answer following the rule of the last operation. Short way of saying, for combinations, you have to apply the last operation, the rule for the last operation. Since the last operation is subtraction, so we have to apply the rules in subtraction. In subtraction, we consider the fewest decimal place after the decimal point. And if we count this, if we count the decimal places in the following numbers, 8.3104 has four decimal places. 8.02 has two decimal places. So the final answer must only contain two decimal places. So we have to round off 0.2904 into 0.29. So another problem is, what if the last operation is division? Then we simply follow the rules for division. In division, the rule is follow the fewest significant figures. So for example, we have 15.803 minus 4.76 divided by 9.3. First, calculate whatever is inside the parentheses. After that, divide by 9.3. And the last operation is division. So we have to follow the rules of the last operation. The last operation is division, and that's we're looking for the fewest significant figure now. 11.043 has 5, 9.3 has 2. Therefore, the final answer must only contain two decimal places or two significant figures. I mean, okay, so that would be all for this topic. If you want to practice what we just have learned, copy this and practice counting the number of significant figures in your notebook. Also, the application of the rules of significant figures in addition, subtraction, multiplication, and division. So that would be all. Thank you for listening.